gravitational waves and gamma rays from binary neutron star mergers. Okay. So we now know that the speed of gravitational waves and speed of light are almost the same. I mean, difference should be smaller than 10 to minus 15 or something like that. Okay. So this implies many things to gravitational theories. For example, in the Hordensky theory, which is a scalar tensor theory with second order equation of motion. So if we try to use this as a source of acceleration, in which time derivative is non-vanishing, then so originally we had 4 free functions starting from P and G3 and G4 and G5, and but among them 2 functions are strongly constrained. But still, we still have 2 functions, G2 or P and G3. Okay. And the situation is similar for the so-called generalized Proctor theory, which is a vector tensor theories. We had originally 6 or more functions, but 2 of them are strongly constrained now. Okay. That's great progress. And also for the Horava-Lifshitz gravity, which is today's subject of talk, of my talk. So in this case, the speed of gravitational waves is controlled by the coefficient of the 3-dimensional curvature. So this coefficient is strongly constrained. Okay. So this probably means that we need to have a kind of IR fixed point where this equality holds, so that as we go down to low energy, this constraint is automatically satisfied. But if we did the case, then we need to speed up the RG flow, because typically we expect to have a very slow RG running. Okay. Typically, especially because gravity is weak. Okay. And and also for the ghost condensate, which is the simplest Higgs phase of gravity, fortunately or unfortunately, this doesn't give us the additional constraint. Okay. In the case of massive gravity, which is, so to speak, the simplest modification of GR, in this case, this implies that we have an upper bound on the graviton mass, which is around 10 to minus 22 electron volt. Okay. Unfortunately, or fortunately, this is much weaker than the requirement from acceleration. I mean, in order to explain the acceleration of the universe, we need to have a graviton mass of order 10 to minus 30, 31, 32, or something like that. Okay. Anyway, so I should mention here that all gravity theories, including general relativity, suffers from the so-called cosmological constant problem. And this is a problem of 10 to minus 120. And this is so difficult that the people tend to forget about this. Of course, some brave people try to solve it. And, so this problem is difficult, but not so, as difficult as this. So I think this is a very good situation. And we don't need to forget about this. I think we can try to solve it within some context. Okay. For example, in the case of Horava-Lifshitz gravity, we need to find the IR fixed point like this. Okay. So this is a very nice situation. Okay. So today's talk is about Horava-Lifshitz gravity, but I'm not going to talk about this. Instead, I'd like to talk about cosmology. So, okay. So this Horava-Lifshitz gravity was originally introduced as a power counting renormalizable theory of gravity. So let me remind you what power counting means. I think I don't need to explain this for this audience, but just as a warm-up, let me do that. Okay. So let's consider scalar field with a kinetic term like this, phi dot square. And then we assign the scaling dimension to this scalar field in the following way. I mean, everyone knows, of course. Okay, let's consider multiplying the time coordinate by some factor b, and the spatial coordinate by the same factor b. Okay. Then let's suppose that the phi scalar field scales like this, where s is some number to be determined. Okay. And we demand that this is invariant under scaling. So we have 1 factor of b from dt, and 3 factors of b from the volume, and 2 factors of minus 2 from the 2 time derivatives, because time goes to denominator, and 2 phi's gives us 2s. Then they must sum us to 0. We have s equal minus 1. Namely, the scalar field scales like energy, as we know. And when we have an interaction like this, phi to n, this scales like this. okay, as we change energy scale, typically. So this minus comes from this minus 1, and 1 from dt, 3 from volume, and ns from n5. And so if n is smaller than or equal to 4, then this doesn't blow up as we increase energy scale. And so we have enormalizability. Unfortunately, when we talk about gravity, gravity is highly nonlinear. When we compute, for example, curvature, we need a crystal field symbol and also inverse of metric. Inverse of metric includes infinite number of terms, okay, if we expand around Minkowski. So the gravity is highly nonlinear. N is, of course, higher than 4. So we have theory which is non-renormalizable. Okay, this is the usual story. The idea of Horava is very simple, okay, but kind of dangerous. Okay, so let me explain this. So let's consider phi dot square again, but define scaling. Okay, let's imagine that space coordinate is multiplied by b, but time coordinate is multiplied by b to z, where z is some number which is part of the definition of the theory. Okay, say z could be 1, 2, or 3. Later, I'd like to consider z equals 3 for the reason that will be clear soon. Okay, and so let's do the same thing. So from dt, we get z because we have z here, and from volume, we have 3. From 2 time derivatives, we have minus 2z. Then S is given by this formula. Of course, if z equals 1, we get the previous formula. S is minus 1. But what is interesting here is that if z equals 3, S equals 0. So the scalar field doesn't scale when we change energy scale, if z equals 3. Okay. So let's consider this kind of interaction again. And from dt, we get z. And we have, instead of minus 1, we have minus 1 over z because of this minus z here. Okay? And the rest is the same. But if z equals 3, then the S equals 0, and this number is always negative. Okay? So as we change energy, as we increase the energy scale, this doesn't blow up. So for z equals 3, any nonlinear interactions are renormalizable. Okay? This is the idea of Horava gravity. So if gravity behaves like this, then the theory may become, gravity may become renormalizable at the level of the field theory. Okay? This is the basic idea, very simple. Okay? So this theory realizes z equals 3 scaling in the UV, and therefore is power counting renormalizable. And recently, renormalizability in the real sense was proved by those people in any number of dimensions. Okay? So we now have a field theory of gravity which is renormalizable. Also, because in this theory there is no higher time derivatives, there is no Ostrogorski ghost, and probably this theory is likely to be unitary. Okay.
Sorry?
Yes?
You could play the same game with the x and leave t.
Mm-hmm.
So
yeah, then we have higher time derivative. Okay. We end up with Ostrogorski ghost. Yeah. Okay. And also in 2+1 dimensions, this theory is shown to be asymptotically free. So this is UV complete in 2+1 dimensions. In 3+1, we don't know, but there may be a hope. Okay. A price to pay is, of course, the Lorentz invariance is broken in the UV. So we need to recover Lorentz invariance in the IR. Okay. So one possible idea is as follows. So as people like Nielsen argued some time ago, Lorentz invariant IR fixed point may be generic. Okay. If we start from theory with define the speed of propagation and run the RG flow towards IR, then they tend to agree automatically under certain condition. Okay. The problem is that this running is a bit slow, logarithmic. So we need to speed up. By the way, this idea may be applied to the speed of gravitational waves, so that this constraint may be realized. But no one has yet analyzed I want to do at some point. Anyway, so in both cases, the running is expected to be very slow, logarithmic. So we need to speed up. There are some ideas, and not yet fully understood, but one idea is Suji. And so if we consider Lorentz violating version of Suji, so we can remove the generator of the boost from Suji algebra, n equal 1 Suji algebra, it still closes. And if we do that, then combining this with the symmetry of the standard model extension has only the, I forgot, Lorentz violating operator from the dimension 5, I think. Dimension 4 and dimension 3 are forbidden. So it's suppressed. And dimension 5 can be forbidden by say, CPT. And then we start from dimension 6. If it is suppressed by 10 to, I forgot, 12 GeV or something, then everything is fine, or something like that. And also, if there is kind of strong coupling between the UV scale and IR scale, then the intermediate scale, we may have a speed up of the RG flow. Okay. So there are some ideas to speed up the RG flow towards Lorentz invariant RF fixed point. Okay. But today, I'd like to talk about cosmology. And there are many interesting things. For example, Z equals 3 scaling can solve the horizon problem and leads to scale invariant cosmological perturbation, even without inflation. Of course, we can accommodate inflation, but we don't need to. Okay. Also, the higher curvature terms may lead to regular bounds, and the higher curvature terms might make the flatness problem milder, even may solve it, okay, and so on. Okay. So today I'd like to talk about these two, horizon problem and flatness problem. Okay. Let me start with this, horizon problem. Okay. So question is this, very simple. Where are we from? And we know the answer. Answer is prime order fluctuations. And associated with this, we have two issues. One is the horizon problem, and the other is scale invariance. Okay. And we need to know why the correlation length of the CMB is much longer than the size of the horizon at the decoupling. And also we need to know why spectrum of prime order fluctuation is almost scale invariant. Okay. In the usual case, both issues lead to inflation, as we know. Let me explain this. Everyone knows, but just as a warm-up. Okay. So in cosmology, we consider homogeneous isotropic universe and the perturbation around it. And perturbation is decomposed into Fourier modes, and each Fourier mode is characterized by frequency omega. Okay? When omega is much larger than Happle expansion rate, then that mode doesn't care the expansion of the universe, just oscillate. Okay? Just oscillate. They don't care expansion of the universe. But in the opposite case, the expansion of the universe plays the role of the friction, and that mode freezes. Okay? What we want is freeze out after oscillation. This is the generation of superhorizon fluctuation. Okay? This can happen if and only if the right-hand side divided by left-hand side is increasing function of time. Okay? By plugging the usual dispersion relation, omega square is k square over a square, where a is the scale factor. By plugging this to here, then we get this condition. Okay? Second derivative of scale factor must be positive. Namely, we need acceleration, namely inflation. Okay? Generation of superhorizon fluctuation requires accelerated expansion, namely inflation, as we know. Also, scale invariance requires inflation. Okay? We know that the scalar field scales like energy, okay? B to minus 1, B to minus 1 here. So the amplitude of quantum fluctuation phi scalar field is expected to be the energy scale of the system. In this case, Happle expansion rate. Okay. The scale invariance means that the amplitude of this guy is the same for different scales. And in cosmology, the fluctuations at different scales are created at different time. Okay. If the fluctuation is created at the earlier time, then there is a lot of time to expand. So that corresponds to large scale. And the mode that is created at late time has only a small, little time to expand, so that corresponds to short scale. And so this means that the amplitude of this guy at defined time should be the same. Namely, Hubble must be constant. Okay? And Hubble is defined by this. By setting this to be constant, we have exponential. That's why we need inflation. Okay? But the story is different if z equals 3. Okay? So this condition is the same. Okay? We want to have oscillation after, freeze out after oscillation. So we need to have this condition. Okay? But if z equals 3, the dispersion relation is different. Okay? So z equals 3 means that time is cubic of space, meaning that the omega square must be proportional to k to 6 divided by a to 6. Okay? By plugging this to here, what we get is this. Okay? Second derivative of the volume of the universe should be positive. Okay? So for example, if we have a power law expansion with p larger than 1/3, p does not have to be larger than 1. Okay? Without acceleration, we can generate the superhorizon fluctuation. Okay? Also, scale invariance is automatic. Okay? We know that the scalar field doesn't scale as we change the scale of the, say energy scale. Then this means that the amplitude of fluctuation does not care the energy scale of the system. And this means that when we change the Hubble scale, the amplitude doesn't change. Okay? We can explicitly compute the mode functions and compute the power spectrum to show that this is invariant, does not depend on the Hubble parameter. Okay? So the scale invariance is automatic. Also, we can apply this idea to tensor perturbation, and power spectrum of gravitational waves is like this, where m is given by this scale. Okay, the scale suppressing the k to 6, okay, and divided by Planck scale. Okay, so this is what is going on. Okay, so this is the size of the universe. This is the scale. Okay, wavelengths of the mode just goes like this. And at low energy, when the Hubble expansion rate is much smaller than the scale that determines this dispersion relation, then of course we go back to the usual story, and we have z equal 1. If we consider just this is at high energy, but at low energy, the relevant deformation becomes important, and we have k to 4 and k squared. Okay, so at low energy, we have z equal 1 scaling. So the Hubble expansion, Hubble horizon and sound horizon agrees. So the scale just comes back to the horizon. Okay. But in the early universe, when Hubble expansion rate is much larger than this scale, then the sound horizon, which is defined by the h squared is omega square, namely that this, when we set this to be 1, that defines sound horizon. And sound horizon is defined from Hubble horizon and goes like this. So if p is larger than 1/3, but p does not have to be larger than 1, and the scale can exit the horizon, sound horizon. Okay, then it frees out and comes back. Okay, this is what is going on here. So in this way, based on the new quantum gravity theory, we have a new mechanism of prime model fluctuation. So horizon problem can be solved, and the scale invariance is guaranteed, and almost. And if we want a slight scale dependence is calculable, I'm lazy enough not to compute this, but in principle, it should be possible. Okay, and also we can compute the non-Gaussianity, 3-point function and 4-point functions, and this predicts relatively large non-Gaussianity, which is consistent with Planck, but does not. Maybe detected in the future. Yeah, I computed this, I can say. Okay, so next I'd like to talk about the flatness problem. But before that, how many minutes do I have? If I have time, I want to talk a little bit about analog of Einstein screening. Yeah, 25 minutes. Okay, good. Let me talk about this. Thank you very much. Yes. So I'd like to talk about analog of Einstein screening in the projectable version of the Horava-Lifshitz gravity. Okay, so Horava-Lifshitz gravity has several versions, mainly projectable and non-projectable version. Okay, in the projectable case, we have a lapse function which is function of time. Okay, at the level of the theory, not only the solution, but also at the level of the theory. And this is a version for which renormalizability was proved recently. So there is a good motivation. And in this theory, the kinetic term for graviton has two terms, Kij, and K square, and where Kij is the extrinsic curvature, namely basically the time derivative of the three-dimensional metric. And in GR, this parameter lambda is 1 because of the 4D differ. But here, because of less symmetry, lambda is a free parameter. Okay? And we want to recover GR in the IR. So we want to have a IR fixed point where lambda goes to 1. Okay? That is our hope. No one has yet computed the RG, beta functions and the RG flow, but that is what we hope. Okay? If it is the case, then we need to send lambda to be 1 at low energy. But if we do that, then the perturbative expansion completely breaks down, as I will explain later. And so we need to do analysis non-perturbatively. We cannot rely on perturbative expansion. Okay? And fortunately, if we do that, then this limit is continuous, and GR is recovered continuously. Okay? So here is what is going on. Okay? So this is the schematic picture of the action for scalar graviton around Minkowski background. And theta is a scalar graviton, basically curvature perturbation. Okay? And this has a kinetic term, theta dot square, divided by lambda minus 1. We want to send lambda to 1. And also, we have this combination where f is a nonlinear function, very, very nonlinear function, and of this combination. Okay? So when lambda goes to 1, this blows up, meaning that the terms with the higher order in theta is more important than lower order terms. So this is what I mean by breakdown of the perturbative expansion. Okay. But as you see from here, lambda appears only in the kinetic term. Okay. Lambda never enters potential terms and gradient terms, and also matter action is independent of lambda. So if we can somehow canonically normalize this part, then because lambda minus 1 is in the denominator of the kinetic term, lambda minus 1 should go to numerator of here and here. And when we send lambda to 1, they disappear. Okay? So in the end, if we canonically normalize scalar graviton, we have just a time kinetic term. Sound speed is 0, and there's no interaction with matter. Okay? This is like dark matter. Okay, anyway, by the way. And so the bottom line here is that canonically normalized scalar graviton decouples from the rest of the world. Okay? So this is basically the analog of the so-called Einstein screening that happens in massive gravity and many other modified gravities such as Galileans and so on. Okay. So this is what is going on. But actual computation is not easy, and because this must be non-perturbative. And for some simple cases, we can do. For example, spherical symmetric static vacuum case, we can show that the limit is continuous and the GR solution is recovered. Okay. Actually, GR plus, no, in this case, GR because static. Okay. If we consider a spherical symmetric dynamical vacuum solution and sending the lambda to 1, then we can recover GR plus actually dark matter. Okay. This guy can be dynamical, and this has a property of dark matter because sound speed is 0 and pressure is also 0. Okay. And I did computation, but I haven't. I'm lazy enough not to write a paper. Okay, I have to write the paper. Okay. And also if we consider spherical symmetric static with matter, then the same conclusion. Also, interestingly, if we consider large-scale perturbations around cosmological background, then we can analyze the nonlinear perturbation by using the so-called gradient expansion method. And then we can show that this limit is recovered. I mean, this limit is continuous and GR plus dark matter is recovered. Okay. So there are many examples which supports this picture. But from this, it's almost obvious that we recover GR plus something like dark matter. Okay. Also, the analog of the Weinstein radius, I mean, Weinstein radius is radius within which we recover GR. Okay. And this depends on lambda. And as we send lambda to 1, this radius becomes larger and larger. And we can cover the, for example, solar system or whole universe if we want. Okay. If lambda is small enough. I mean, deviation from of lambda from 1 is small enough. Okay. Okay, let me go back to cosmology, flatness problem. Okay. So I'd like to first remind you that there are two difficult problems associated with the Friedman equation. Okay, this is a Friedman equation. And one is a cosmology constant problem. The second is a flatness problem. Of course, the most difficult problem is the cosmology constant problem because in the right-hand side, only lambda doesn't decay. Other terms decays. But we need to explain why lambda is as small as other terms now. Okay. So cosmology constant problem is the most difficult problem associated with this. Okay. If we can solve the cosmology constant problem, I mean, in the future, then the second most difficult problem is flatness problem. Because let's set this to be 0 for some reason. Okay. Then this curvature term decays like 1 over a squared, but other terms decays like 1 over a cubed, a to 4. So this decays, but slower than others. But still, we need to explain why this is smaller than other terms. Okay? So that's why I'm saying that the flatness problem is the second most difficult problem associated with the Friedman equation. Okay? In this talk, I'd like to consider the flatness problem. Unfortunately, I don't have a good idea to solve the cosmology constant problem, so I'd like to concentrate on this. But this is what inflation does. Okay? Inflation doesn't solve the cosmology constant problem, but can solve the flatness problem. Okay? So I think there are at least two ways to tackle flatness problem. Okay, I set lambda to be 0 because I declare not to solve the cosmology constant problem. Okay? First one is, of course, inflation. Inflation says that this energy density does not decay for an extended period. Then for that period, this still decays. This is slow, I mean, decay is slow, but still decays. And if we wait for a long time, enough time, then this becomes so small at the end of inflation, then it takes long time for this guy to catch up. And this guy has not yet catched up the other times. Now, not yet now. So this is how inflation solves the flatness problem. Okay. But what if this is very small initially when universe was created from the beginning? Okay. This would be the quantum cosmology solution. Okay. If some quantum gravity theory tells us that this must be smaller, much smaller than this, then that's it. Okay. This is a very simple solution, if it works. Of course, today I'd like to talk about this second possibility, because we now have some interesting quantum gravity theory. Okay. Usually, of course, this doesn't solve the cosmology, flatness problem, okay, as we know. Okay. So if we consider some quantum cosmology, then initial condition it must be set by some quantum gravity process, such as quantum tunneling. Okay. And we know that in the absence of gravity, the quantum tunneling is dominated by all-force symmetric instanton. Okay. In the presence of gravity, we don't know, but there is no proof. But most of us think that all-force symmetric instanton still dominates. Okay. This implies that all-force symmetry means that time and space in the Euclidean space are the same. Okay. So time scale of the instanton and the length scale of the instanton must be the same in the Euclidean signature. After nucleation, namely after analytic continuation, the time scale is 1 over Hubble parameter, of course, and the length scale would be curvature scale, of course. And this means that these two are the same, and looking at this Friedman equation, all three terms should be the same order. Okay. If we consider compact space, then the k must be positive, so this term is negative, and there's the same order, so 3 must be the same. Okay. So we have a flatness problem, okay, unless inflation occurs. So this doesn't work in the usual case. But the situation is totally different if z equals 3. Okay. This is the same. So initial condition must be set by some quantum gravity process, such as quantum tunneling. But now, we don't have O4 symmetry. Instead, I think we should respect z equals 3 anisotropic scaling because, yes, because we have a theory that realizes z equals 3 scaling. And this is the reason why we have renormalizability. Okay? So z equals 3 scaling means that the time scale is cubic of length scale. And after nucleation, of course, the time scale is given by 1 over h. And L is a curvature scale. Okay. And by putting some energy scale, m, which is, sorry, I should have written here. M is basically, sorry, the same as this one. Okay. Scale that defines the dispersion relation. Sorry. Yes. Then we have this relation. Okay. If the time scale is much smaller than this, sorry, I'm sorry. If the length scale of the instanton is much smaller than 1 over m, then the time scale is even smaller. Okay. This is exactly what we need for the solution to the flatness problem. I mean, instanton is like this. Spatial scale is very, very long compared to the time scale. Okay. This is exactly what we need. And so flatness problem may be solved if the anisotropic instanton is small. Okay. So, okay, let me summarize. And Horava-Lifshitz gravity is renormalizable and likely to be unitary, and therefore a candidate for UV complete theory of quantum gravity. Okay. And Lorentz invariance can be restored at IR fixed point, and Suji and strong dynamics may speed up the RG running towards the IR fixed point to match with the phenomenology. And it is likely that GR plus something like dark matter is recovered in this limit, where we expect to have a GR, something like GR, due to nonlinear effects. I mean, this never happens at the linear level. We need to take into account nonlinearity. Okay. And horizon problem can be solved, and almost scale invariant cosmological perturbation can be generated without inflation. Okay. And the flatness problem can be solved by equipartition in highly trans-Planckian regime. Okay. And how many minutes do I have? Okay.
You have
10 minutes. Okay. Maybe if I have time, may I talk about this maybe in 5 minutes? Or do I have to move on to the question and the comments? What do you think? 5?
If you'd like to speak about it.
Okay. Yeah. Let me then briefly talk about this. Okay. So this is a walk down with those people and about gravitational collapse in the Einstein ether theory. Einstein ether theory is a low energy limit of the non-projectable version of Horava-Lifshitz gravity. I mean, as I said, the renormalizability of Horava gravity was proved for the projectable case, but non-projectable case may also be renormalizable, and the proof has not yet been done, but yes. Anyway, so this theory is a low energy limit of non-projectable Horava-Lifshitz gravity. And also so this may be useful for test of GR, because this is a GR plus time-like unique vector representing Lorentz violating gravity. Okay. And this theory has GR action plus 4 parameters given by this. Don't worry about these formulas. We just have four parameters. Okay. Okay. C1, C2, C3, and C4. And there are some formulas, and let me just go here. And we have constraints from on those parameters. Okay. First, the strongest constraint comes from this event. Again, so this combination C1, 3, which is the sum of C1 and C3, must be smaller than this. This is a very strong constraint. And other constraints like BBN, PPN, and pulsars, and stability, and Gravi-Cherenkov, and so on, are decomposed into 2 categories. One of them is written in this plane. The other one is written in this plane. Okay. And so this is a constraint on this plane, C2 and C14, and this region is arrowed. Okay. And on this plane, the constraint is simple, so I didn't plot. Okay. Anyway, so we wanted to consider gravitational collapse within, for example, somewhere in this narrow region. Okay. And in Lorentz violating gravity, such as Horava-Lifshitz or Einstein ether, the concept of black hole is unusual and interesting. And so because light cone structure is only emergent IR, in the IR. In the UV, there is no concept of light cone. Only at low energy we have light cone. Okay. So the usual event horizon or apparent horizon are also emergent. And however, the causal structure in the sense of past and the future still exists because we have a kind of clock field, sometimes called chronon. And also, there may be still, the absolute causal boundary for the universal horizon, from which nothing can escape. Okay. So this is a schematic picture of the so-called universal horizon. And this is a constant time surface represented by the clock field or a chronon. Okay. And this is the radius. And this constant time surface does not, penetrate beyond this radius. Okay. In this case, this radius is called the universal horizon. Okay. Okay. And we wanted to know whether universal horizon can form from gravitational collapse. So we need to do some numerical study. And for simplicity, we consider massless scalar field with a spherical symmetry. Okay. And let me skip the details. We defined the dynamical version of the universal horizon here, and but let me skip this. Okay. And some numerical results. So this shows that the pair of apparent horizon forms, and the outer apparent horizon becomes stationary. Okay, this is the outer horizon, and okay, so this is expansion basically along the null line. So there are apparent horizon here and here, and outer horizon becomes stationary. Okay, and also the dynamical version of universal horizon keep forming outside the outermost dynamical universal horizon. So we have a multiple of the dynamical universal horizon. Let me skip this. Okay. And what is interesting is that the proper distance between the outermost dynamical universal horizon and the outer apparent horizon also grows. So this dynamical universal horizon is approaching to the, seems that this is approaching to the kind of, the causal boundary. Okay. So it's difficult to penetrate. Okay. Anyway, so we performed a numerical study of gravitational collapse of a massless scalar with spherical symmetry, and apparent horizon and dynamical universal horizon form, and the geometry outside outer apparent horizon becomes stationary, and the proper distance between the outer apparent horizon and the outermost dynamical universal horizon along the ether orthogonal slicing keep increasing. Okay, so okay. Maybe I skip. Okay. Yeah, I'll finish here. So.